Oh, you pay money. That makes sense.
So I'm just trying to like.
So I feel like you're in class every other day. We only have quizzes. We do only have one.
It's probably taking
Two packets for, so like a packet for each exam, like each to like retake. So 2 packets each exam, like quizzes every Friday. My homework is like huge because I have to use a page for every single problem. And like I have to do 3 problems per topic. There's usually 4 topics, so class.
Yeah.
Like once I get it adds up, and like you have to write a bunch. Like
Alright guys, so today's goal is to finish our in-class number 12. So you know how to measure frequency from the input signal. And then, if we still have time, I'm going to answer some questions of the PCB, the course projects. And for Friday, we'll just come to this classroom and you guys work on your project or PCB and any other things you have to work on. It'll be a tutoring session. And on Monday, we'll do our final work on the final tutorial, which is IC Current and SPI. The reason I still want to cover, I know you haven't finished anything about the tutorial 6 yet, but I still want to cover, do the lecture on tutorial 7 and get everything recorded, so you can always come back and revisit. And we can also do our in-class number 13 and 14. Okay, so we are done for the semester for all the lectures and new materials. Okay, so I'll give you the time to you after that. Right. So measure frequency. Since we know the sampling rate, and there will be a chance to measure the frequency. So for task 1 for this ADC, even though you haven't done that yet, but it's mostly given for the code, right? So the setup is given, the timer ISRs are given, so you just need to do some work on the variable declarations, okay? For this one, it's not tricky at all, right? And then for task 2, so the differences between task 1 and task 2 is for task 1 it's only recording I think 16 variables. Let me see, I couldn't remember, but it doesn't really matter. So this is probably only recording 16 data points, and then you plot it, right? Before task 2 is asking you to record 256 data points and printed them out in the serial monitor in a certain pattern. And here comes the question number 1 on in-class number 12. Do you all have a copy of it? Anyone doesn't have a copy? I still have a copy here. All right. So let's start with question number 1 first. So if I define the code, the sample period, right? Just do a define sample period to be 25. Remember the sampling rate. I'm taking every 25 microseconds to sample 1 point. But as a variable, right? As a constant, it's very difficult to put a 25 times 10 to the negative 6 over there, right? So what we usually do is I define that period to be a 25 is actually 1,000,000 times larger than what it should be, and the unit is microseconds, right? So what the sample frequency should be, so I put a define, the hashtag define sample period and then 25, and then I start define the sample frequency, right? So I do a hashtag sample frequency. So how should I define that? Let me write it down on the paper, just in case you are not getting that. Oh, it's over here, right? It's over here. So if I have sample period, sample frequency, so I do this, right? I do this. Now I'm trying to define sample frequency. It's not a unique way to do it, but I'm just showing one of the ways to do it, right? So for sample frequency, I'm trying to use this one will be larger than 1, but this one in real life, it's 25 times 10 to the negative 6, right? But the thing is, but how to do this if it's gonna use a second as a unit? So instead of doing that, we could use 1 million divided by 25, or divided by sample period, okay, which is already defined up here. Why? Because 1 over 25 times 10 to the negative 6 is actually, you flip this to the top, it's going to be 1 million divided by 25. Just very simple algebra. So that's how you can declare your period and sample frequency. You can use it for the code. So we come back to this result being printed to the serial monitor. I can see every 16 points, I start a line with the line number. So the way I format this line number is, it's S, right? S represents send probably, or signal. So it's a signal 0. So S bracket signal 0. So it's a S bracket 0. Okay, and for the next one, because the first one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and 0 to 15, and the 16 to 31. That's how I define it. But the first column to be printed out, the first column will be the line number. But I format the line number as capitalized S with a bracket with a 0. It's just something you want to print it out. It's just a character to be printed out, including the bracket. And so I'm asking you guys to write that code to print out these line numbers in this certain format. Now, why we have to do this? It's just one of the tasks, right? To practice on how to print out a certain format in a serial monitor. And let me see if I gave this to you already. I did. Guys, over here. How that works? You can see every time, whenever it's the. So, for example, if the index reaching a multiples of 16s, including 1, right, and 0, it changes the line and printing out another 16. So it has to be an if statement to check something. So the way we check it is, because it's multiples of 16s, right? So what we can do is when so it's going to be if, right? If I and 0x 0f is 0, they'll do something. So basically, whenever this is printing out all the numbers, the sampled numbers, see here? So it's printing one by one. You're doing an increment to the I every time, right? So whenever it reaches 15, but basically the 16th number, because this number is 15, right? It's 15. So when I becomes multiples of 15, since it started from 0, but basically it's actually reaching the 16th number, you change the line. So whenever to change the line, you can use this and place it in front of the ones you want to print it out. that's the number in the bracket. It's gonna be like this. So you want to change the line first. So slash R will return, right? Return, and that's the new line, right? So the new line, and also you return the cursor to the front of the line. So slash R slash N. So do this in front of that bracket. I think you need to do as here as well, as. Because you look at the format, you don't have the in class 12, but I have one copy here if you don't have it. Just take it, it's okay. You see, starting from 0, because I started with 0, right? I started with 0. So 0 and this one definitely will be 0. So that is why at the very beginning it prints out this first, right? Because I was 0 at the very beginning. So this is the very first thing to be printed out. And that format is defined by this. Okay? It starts a new line and print out the S first, and then the bracket, and inside the bracket it's a variable. So if you want to do a variable here, if you have to use the specifiers for C, and that's why you use this, because these are all decimal numbers. So before you end it, you need to put a number here, as a variable here, and that's your buffer, right? Print buffer. I'll let you guys complete it, but it's just showing the concept. Everything here is included in the as printf, right, like this. So what variable should be plugged in here if I want to print it in this way? It's being printed in the buffer first, right, with a certain format, and this is your format. And that variable should be printed over here, and that variable, because this question is different from the one of the tutorial, right? This is a different question. It's asking you to print out numbers from 1 to 64 in 4 lines, right? In 4 lines. So every line should be 16, right? So it's 1 to 16 for the first line, and then 17 to 32 for the second line. So you can still use this condition when you have a for loop, right? The for loop outside of it. So I will start from 1, right? From 1, and then you do a condition if it's less than what, and then do increment. Right? Think about it. Think about it. So it's looping through, right? So, but whenever I reaches, will this work? It reaches 1, and this one won't be 0. So it should be I minus 1. Are you getting that? What I'm saying?
I think that makes sense.
Mm-hmm.
Why wouldn't you just start before loop at I equals 0?
That should work as well, I think. Yeah, either way.
That'll,
Right? Because the first, so the expected result is you are printing out 0, right? And then 1 to 16. Then 1, 17 to 31, 32. And then 3, 33 to 48. And 4, 47 to 64, right? So that's the expected results. That's the expected result. in that case, you are looping through so that you are actually printing out. Let's see, what should we do? So for I, if I is 1, when I is less than 65, you should do this, right? It's keep printing. So it's just printing out 1 to 64. Everyone can do this, right? Just use a for loop to print out 1 to 64. Easy. Okay? So that's the for loop you want to use. And when it's printing, you want to check whenever it reaches 16's multiples. And you want to print a line number here. And you don't have to put an I here since it's not asking you to put S, right? So it's just a bracket and with a variable here. And that should be a change the line with this. And what about this guy here? What about this guy? So let's look at the first line. If the first line I starts with 1, right? And I minus 0, so 1 minus 1 is 0. And you're getting 0, you enter here. What about here? Should be the line number here should be 0, right? Should be 0. Should be 0. But now your I is 1. Right? So that works for the first line. Right? But for other lines, when I is 16, you print out 16, no problem. So you have to, after this one, you have to do, because this one checks this if statement, but you have else as well. Outside of the if statement, you want to do
Why not just index the lines from 1? Why not just index the lines from 1 instead of indexing
Here?
from 0? No, I just mean like in your print.
That's fine, either way. What did I ask you here? Print a line number. It could be 1, yep. It won't be exactly the same as the example over here, but if you could change it to 1, right? Since we're right here, so following this pattern, so let's just keep it 0. Otherwise, I have to change everything right now. So for this one, if it satisfies this line changing, you have to break the line. You do this. If it's not doing a line breaking, it's outside of this if statement. It's right here, right? So you want to directly just print it out, right? That will be just do the buffer printing out, and you're just printing out the number, right? Just print out the number. So I here. So if it satisfies this, let's see what's gonna happen. If we have I is 1, this is 0, it satisfies, comes to here, you print out the 0 first, and then comes out, printing out the 1, right? So that works for this case. 0, 1. Does that make sense? If I is 0, yeah, but if I is 1. If I is 1, right? If I is 1, this one satisfies, starting from the very first line, very first number, this be satisfied, getting satisfied, and print it out. I didn't include a serial print, but just printing to the buffer, okay? So this one got to satisfy, print out the line number, which is 0. So start with 0, and then get out from this if statement, we'll print out the number, just following this number, just follow, right? So it becomes, it's printing out this and 1. And for all the following numbers, it doesn't satisfy this anymore. So directly jump to here and print out the number. What that number is, we'll directly print out that number. So it's gonna keep doing this until what? So print out 16. 16 comes down here. Doesn't satisfy because 16 minus 1 is 15. 15 and this one is
I'll click on 17. So you need to change
yeah.
that to
So
15.
17.
So that should be an E.
Hmm?
If you put an E there.
No, 15. 16 doesn't work, right?
I minus 1.
Oh,
and
16 works
an
actually.
E.
16 works. $16 works actually. Is that
Back
correct?
to 16 and then on 17 it'll switch and print 16 in the.
So yeah, so this guy is 0, 0, 0, 0, 1, 1, 1, 1, right? So I minus 1 has to be exactly this number to make it work. Wait. So if I have if I is 16, 16 minus 1 is 15, that wouldn't work, right? But 17 will work. So if 17 minus 1 is going to be 16, will be this. So the lower 4 bits become 0, and with this mask, it becomes 0. So whenever it reaches 17, it will print out the line break first, and then print out 17. Here,
It'll print out 16
or print out 16, yeah.
in the row.
So this should be,
and then it'll start at 17. After that. That's right.
yeah, this is 17, right?
Yeah.
Yeah. So we'll print out that letter here, the number here first, and then 17. If it works for the 2 lines, it should work for the following lines as well, right? So I'll let you guys organize this a little bit. I'll give you a few minutes after it's approaching the end of the lecture. I'll let you guys. It's almost there. It's almost done. Any question on this? I'll give you several minutes. So now you can take the notes here, but you know, at the end of the lecture, I'll give you several minutes to finish it. Okay. For question number 3. You know, so what we are going to do is sample that whistling. So it turns out to be a signal like this. Okay. And our task here is to measure the frequency and report the frequency of it. Some students are proposing an idea of the course project by checking the input signal's frequency and output that frequency and convert it to an intensity of the PWM being sent to the RGB LEDs to change the intensity of the RGB LED. So you can use the RGB lights to show the intensity or the pitch of the input sound signal. But in that case, you need to measure the frequency or intensity of the signal, right? So to measure the intensity, you are using ADCs to sample the voltages. To measure the frequency is whatever we are going to do for this tutorial. Okay, how do we measure the frequency? So the points are sampled and placed in the buffer. And we know that the duration of each sample is what? 25 microseconds. That's what we set up for the ADC. Okay, task 1 is already mostly given to you guys, so you know how to set up 25 microseconds for the sampling rate. So for the question number 3, it's telling you that for one period, there are 100 points for one period. And we know that the sampling rate is 25 microseconds, and it's asking you for the period of the sound wave. Yeah, just times 100. You are probably talking about, hey, if I have 3 points, you have 2 intervals. Are you trying to do like 100 minus 1 times 25 microseconds to make it more accurate? Which is fine. You know, who cares? It's just a 125 microseconds difference. But including the errors, it probably doesn't matter at all. Yeah, if you want, you can use 100 minus 1 times 25 microseconds. If you don't want to do so, it's okay. It's not a big deal at all, right? So if there are, so the way we measure it is in your code, right? If we have 1, 2, 3, I want to let you guys think about it first. So what the ADC can do is just sample a bunch of points, maybe hundreds of points, and store the points in the buffer, right? So eventually, what you got is gonna be all the points, right? You print it out. These are the points the ADC sampled. So basically, just the bytes, right? Just bytes, 8-bit numbers in there. So based on the numbers stored in the buffer, how could you find out the frequency of the sound wave? If I don't give examples, I mean, try to be creative. What are the ways to do it?
Without the samples.
Yeah, just with the samples. You have, so the ADC, what the ADC does is just sample the points and put in the buffer, right? You have all the bytes in there with a different intensity because the sound wave is oscillating. So you are basically sampled all the points and put in the buffer. So based on the values of the sound wave, so what are the ways to measure to get a frequency out of it?
Find every time it meets like the same amplitude value.
But it could be different, right? Because the ADC is not getting you the same value all the time.
Or every time it crosses over a certain
Cross over a certain value, yes, right? So what are the, but what value
Zero.
being crossed?
Probably like the midpoint.
The midpoint will be a good way. So, but what about the peak or bottom? Is that easy to do or no? So what if we are checking the peaks, right? So if you reach 2 peaks, you know that in between the 2 peaks, it's going to be a 1 period. It's 1 actually. It's 1. So between 2 peaks will be 1 period, right? But how do you check a peak? Just based on the values being sampled and put in the buffer. Max, but how? I mean, it won't be a Python, right? CPU or laptop can do it, but you are actually accessing the register level of programming and you are taking out the bytes. It's basically just bytes. I mean, if you are detecting peaks, you could do like the previous one, like I minus 1. So because everything, right, is stored in the buffer, right? You have all the i's as index, right? So if you look at, hey, so I here, the current value here, over here, and the previous one, I minus 1 is less than this one, but I minus 1, I plus 1 is large. Oh no. So I minus 1 and I plus 1 are both smaller than I, right? So that's going to be a peak. I think that should work probably. Okay? For the bottom, right? The bottom will be I minus 1 and I plus 1 are larger than I. So that's the bottom, right? So you can just log that I. So you know that I at that index. For example, this index is a 50. Right? Here, the index is 50. And then I find out another I satisfies that condition, and that index is 101. All right? So in that case, what's the period based on these two values? Right? This is how many points we have. Ignore the plus minus 1 thing. It's okay. So we are assuming that you have this many intervals. And what's the interval? 25 microseconds, right? So we can find the period of that. And then eventually, for example, I detected 3 peaks. This is 203. And now it's asking for a period of the sound wave. and I'm assuming it's a constant frequency. So I'm gonna do an average of these two periods, right? If you detect the 3 points, how many periods do you have over here? If I have 3 points, three bottoms, how many periods? Two periods, right? 1, 2. So if you have 3 bottom peaks, take a 3 minus 1. That's this many periods, and you are using 203 minus 101 plus 101 minus 50, and then for the whole thing, the times 25 microseconds and divided by 3 minus 1. So it's the average period of the sound waves. Okay? That's one way of doing that, but also you can simplify this a little bit by checking the zero process. That's actually the easier way because you don't have to check 2 values. It's just basically 1, right? So still the same thing. And looking at this point and assuming this is 0, so if this one, like here's I, right? Here's I with that value. All these values are stored in the buffer. So if the previous one is less than this value and the next one is larger than this value, so we know it's just crossed this value here, right? And you can log that I over there as well. So but you have to find out the Y over there. But usually for 8-bit, since we are using an 8-bit precision for the ADC, so if you don't turn on anything, just keep it quiet, don't whistle, and just let it sample. It should report because 8 bits is giving you 256 as a range, so it should being set at 128 as a middle line. The reason for that is if you look at the schematic here, look at this guy, right? So this is the microphone. This is required by the microphone. If you look at the data sheet, they require a pull up to the power supply to make it work. You know, we don't have to worry about the internal structure and the physics of the microphone, but you have to put it up to make it work, right? Anyway, so AC signals, because the microphone receives the signal as an AC signal, passes this guy because it's a high pass filter, passes AC but block DC, okay? So the AC comes over, but the op-amp here on the other side, because of the negative feedback, right? And it's gonna make these 2 values equal. I'm pretty sure you forgot how to do it, but what I'm saying is you could lift the AC signal here by a DC offside, and the DC offside is being set up over here. So it's not getting interference between these 2 AC and DC. Nor is if you forgot how to do it, but what I'm saying is AC signal passes this high pass filter, get a pure AC, and that pure AC is being superimposed to the DC being added to the other side of the input. And that DC is what? 5 volts, right? 5 volts goes to here and then goes to 10K resistors and giving you a 50% drop. So that's actually a DC offside of how many volts? It's a voltage divider, right? 10K, 10K. What's the voltage here? 2.5. So the lifting is lifting this AC to 2.5. So it's oscillating around 2.5. That's what we usually do, okay? Because the op-amp is providing a power to ground rail as 5 volts to 0 volts. So you want to swing, you want to oscillate your signal around 2.5. So get maximum range on both sides. That's why you lift it to 2.5. How do you lift it? Lift it on the non-inverting terminal by a DC. You know, it's just fundamentally the standard way of doing that. Okay, so you don't have to like plus and minus dual power supply. It's not 5 and -5. It's only 5 and 0. So I have to add a DC offside to lift it to 2.5 DC, so you can swing your signal around that. And that is why we are swinging our signal, our input signal, analog signal, around that 2.5, and that 2.5 is being provided by this non-inverting terminal, by this voltage divider. Okay, so if you don't have any AC signal over here, this point should give a 2.5 DC to it, right? So 2.5 DC in your ADC here is 50% of the range. So this is 5 volts. This should be 2.5 volts. However, if you don't do anything to it, I don't know if it's something wrong with my resistor's accuracy or something else, but I'm not getting 128 over here. What I'm getting is 160, which is fine. I'm just setting my 0 point to be 160. You can test yours without whistling to it, right? Just see what the static voltage is giving to you, and then you set up your zero cross to that point. So I see 160 for my board. Yours is probably 130, 150, doesn't matter. So you can set it up as your 0 point. So whenever you are checking the zero cross event, and you are checking if you have one number here is less than 160, and another point is larger than 160, and you want to log that number at that index. So that's 1 0 cross. Okay, so you can detect it. If it satisfies this condition, it detects a 0 cross. So if you have 3 0 crosses, how many periods you have in the signal? If you have 3 0 crosses, how many periods do you have over there? 1 0 cross, 1 0 cross? Why and why not?
It is.
This is 1 0 cross. This is the same as this guy. 0 cross or not? It crosses 0, but in the wrong way. Is this a 0 cross? No. Why? Because we are doing whenever it's less than this guy's I minus 1 and this guy's I plus 1. It has to satisfy this. Because I minus 1, which is the previous one, is less. And I plus 1 is larger than 160. So this is 160, okay? So I minus 1 is less than 160, and I plus 1 is larger than 160. It's defined as a 0 cross. What about this guy? Doesn't satisfy because it's I minus 1 is on the top. So it doesn't satisfy. So only this one satisfies, right? If I got 3 0 crosses, what you want to do? Log the index 50, 101, 203, for example. You want to log these indexes immediately, log it, right? And then do a math over here, 101 minus 50 plus 203 minus 101. This many periods for the first period. Is this many intervals for the first period? This many intervals for the second period. Times what? Divided by what? There are sample intervals, right? Intervals. How many for each? How long for each? 25 microseconds. This, how many intervals here? How many intervals here? Times what? Divided by what? Times 25 microseconds divided by
2, 3.
3 minus 1. So 3 is how many 0 crosses? That's easy to find since you detect it every time it crosses a 0, you log it. So you can get a count. Okay, that's how you measure frequency. What about period? Wait, so how could you do microseconds in your code? So the first question is, what is the period? So this guy is actually the period, right? That's a period for each, I mean, just period, right? For each sound wave.
In microseconds.
If you use 25.
Right.
Okay. So that's the answer for the first question. What about frequency in hertz? If you know this, but it's in microseconds, how do I get frequency in hertz?
1 over period.
1 over the period, but the period is in microseconds.
Times million.
So flip it, right? So let's yeah, that's right. So let's flip so you can see this right now, this result over here right now, okay? If you flip it, you're getting 3 minus 1 over 101 minus 50 times 25. But what is the unit here? I mean, keep in mind, that's why we are talking about this. It's all because all the variables are declared as integers. But if you look at this number, is that possible to be an integer? It's a fractional number. It's way less than 1. So integer will output 0 for you. Will this work?
No, because it's not in the.
It won't work because it's not an integer. So you cannot use the integer. We all use integers for as preferred data type for our microcontrollers because the floating point numbers are fractional numbers are a lot of consuming a lot of computation resources. So we never use don't try to not use floating point numbers for 8-bit microcontrollers. Don't do that. If the integer and we flip it, this becomes a megahertz as a unit, right? If it converted to hertz, we have to times just 1 mega, right? It's basically this guy is megahertz, right? So it just move mega here as 1 million, and then it becomes hertz. Does that make sense? Okay. Is this the integer? Very likely, right? Because these are just like few hundreds. This is millions. So you got an integer. You can, it's taking out the integer part of it.
But it doesn't resolve to an integer.
No, I mean it's a fractional number, but it's taking out the integer part.
Oh.
Yeah, so you are fine because it's an integer type, right? So integer type, so it's only store the integer part of it. Okay. 2 pi? Why? 2 pi. Why 2 pi? It's just the period and the frequency. There's nothing about the circle. So that's all about number 12. Now let's go back to the code so you can see if there's something else I'm missing there. All right, a couple things because I changed the deadline for Tutorial 5 Tactical 3 to tonight, and some other things I found from other students, and the IR light, right? It doesn't work well for a black surface. I've done a very similar experiments in the past for circuit 1. Is using an IR pair to detect the track. The track we used was a black tape on the table. So whenever it detects that black tape, it's getting turned off because it's not reflective. So eventually, you have to use a sort of like a light color surface. The similar effects if you use for example, if you put in the box, right, or if you just randomly place your IR light in front of a darker surface, then it won't get a lot of reflected signal, and eventually you are not actually receiving anything. So if you couldn't solve that problem, the easier way to do that is just to place the white paper in front of the emitter, so you can receive a way more reliable signal from the emitter. If you see some error messages, just put a paper in front of it, and probably will fix it. Okay, and that's one thing. Another thing is that happens when you are very close to the truth, right? If you are still far away from the code you need to use, then you have to debug the code first. Okay, so for other things you need to know, just really quick. There are a lot of materials provided to the tutorials and notes. Okay, so I checked with several students' code, and basically a lot of them didn't really follow whatever I put in the lecture. Auto internet. Okay. Anyway, but so the thing is, go to the lecture videos and notes. I already give you a lot of the answers over there. So I check the notes and check the state diagram. The state diagram already give you like 85% of the solution of the code. You could always visit, and so I can check your answer and give you some hints on that. But there's no internet connection, so probably I just want to go through this first, so I'm running out of time. Another thing here is okay, this one. Okay, you print out all the data here, and all these points are stored in the buffer. You start taking out. So these are the indexes, the zero crosses. When the zero crosses happens, these are all the indexes. Okay, all the indexes here. And then I do a subtraction, like what I did on the paper, the subtraction. So you got all the intervals. Are the intervals? You can see it's pretty consistent, like from 19 to 23. It's pretty consistent. So intervals, you times the sample rate of the 25 microseconds. So you can get and then do average, right? Do average in your code. Eventually you can find out the average period of all the sound waves. And you print it out. Again, it should be very close to 2 kHz, or from like 1 point something kHz to 4 kHz first, and second, for 256 points, you are supposed to get like 10 to 12 or 13 periods. If you're only receiving 5, 6, or 1 periods, you want to just move it closer to the microphone and or do it louder, or just play the. If you're using audio resource online, you want to play it louder, okay? And you could copy and paste everything and put it into the Excel sheet and use whatever I put in here. There's an instruction regarding how to split the data into all the columns, and you can plot it. Okay, you have to show that you do got a sound wave from your signal, and so what that does is, whatever I'm showing in the tutorial, right, is checking a zero cross. If the middle line is a zero cross, it's looking at the one before it and the one after it, and then and log that index into your buffer. Okay, so I already gave you the code about how I calculated the frequency. It's so it's over here, right? So this part, Did I give you another one? So that's the only one I gave to you, right? So, but based on the equation over here, like this one, you write the code by yourself for that part, the frequency calculation. To avoid some noise, right? So to avoid some noise, it only starts sampling when it reaches the threshold. So I'm adding a little error to the middle line. I observed a middle line to be 160, so I'm adding the 10 LSBs to that 160. So it's plus minus 10. So that's why you are seeing this upper and lower threshold. So whenever it's lower than this threshold or higher than that threshold, which means the input sound signal is large enough to be logged. So in the SR, I'm checking that to be satisfied first. So I trigger it. So I have to use the if statement. So if the input signal is smaller than the upper threshold, lower threshold, or larger than the upper threshold, I log it. Otherwise, I don't trigger the ADC. So basically, but it's not always checking that state. Whenever the first data satisfies the condition, it will keep logging because it jumps to the acquisition state without coming back. So whenever the first data satisfies, it will stay at the acquisition state and keep sampling all the rest points and log it to the buffer. So the state machine, starting from the idle state, is controlled by the fill the buffer flag. So it's adding one more layer of control over it. Doesn't like task one. It's when you start it, when you part it up, it starts logging data. So this one is waiting for a press on the keyboard, which is F. You press F, this flag becomes true. It does all the state transitions. And this state machine is like 5 times easier than the IR transmission one. So this shouldn't be that tricky over there. If you don't press it, you are going to see just staying there without doing anything. You press F. So what you do is you do a whistling first, and you press F. It will sample all the 256 data points immediately. Okay, very quickly. All right. So the task for this one is basically filling up all these blank areas. And it's just one SR. It's a lot easier than the IR one. And this one is just the ADC conversion to start it. Just one line. It's already given in the task one. So really nothing to be changed. And here a little bit coding here as well to log your index into a array. That's it. Okay. So Friday we'll come over here and it will be a children's session. Okay. We'll meet in this classroom on Friday. That's it for today. Just turning your in class number 12.